All right, so if you're gearing up for a software engineering interview, or honestly, if you just want to know exactly how the internet manages to keep your private data safe, you absolutely need to know this. Okay, let's just dive right into this explainer. We're going to break down the exact mechanics behind literally one of the most common and really most powerful features on the web. Today, we're decoding the OAuth 2.0 authorization code flow.
Think about your own daily internet usage for a second. You go to a new app, let's say a photo printing service, right? And instead of creating a brand new account from scratch, you see that super familiar Continue with Google button. You click it, the browser does its little redirect dance, and boom, suddenly you're securely logged in. But what is the actual system architecture driving that magic behind the scenes? Like, how does that app get your data without ever actually seeing your password?
Well, when your interviewer asks you about this, you've got to establish the technical baseline first, because honestly, people mix these two terms up constantly. Authentication is all about proving who you are. It's just the system verifying your identity. Authorization, on the other hand, determines what you are actually allowed to do once that identity is known. And OAuth 2.0, it's fundamentally an authorization framework. It's all about granting specific, limited permissions.
Think back to the early dark ages of the web. If an application wanted to access your data on some other service, you literally had to just hand over your raw username and password and kind of hope for the best, which obviously is a massive security nightmare. But as highlighted in our sources, OAuth 2.0 acts sort of like finding a secret back door that's guarded by a really strict bouncer. Instead of handing over your raw credentials like it's no big deal, OAuth 2.0 demands this incredibly sophisticated exchange of tokens, redirect URLs, and temporary codes to make sure everything stays totally locked down.
So let's look at how this builds our system. To really grasp the flow, we need to rapidly define the 4 core roles straight from the official RFC 6749 specification. First up is the resource owner. And in almost every single scenario you'll run into, the resource owner is simply you. You're the end user. You are the entity that's actually capable of granting access to your protected resources, like your profile info or your personal photos.
Acting on your behalf is our second role, the client. Now, quick heads up, don't confuse this with a client web browser. In OAuth terminology, the client is the application that is actually requesting the access. Let's use a really great example from our sources. Imagine a printing service called Print Express. Print Express wants to access your photos so it can print them. In this scenario, Print Express is the client.
Okay, so where do your actual photos live? That brings us to the resource server. This is the server that physically hosts the protected data being requested. Going right back to our example, if your photos are stored in Google Drive, well then Google Drive is acting as the resource server. It's the system holding your data, and it is only going to hand it over if the client presents a valid access token.
And finally, we have the authorization server. This is the system that actually verifies your identity and issues the access tokens over to the client. Now, in the real world, the authorization server and the resource server are often run by the exact same company, like Google manages both the login screen and the Google Drive data, but architecturally, they are completely distinct roles with very distinct jobs. And calling out that specific separation is a fantastic way to show senior-level understanding in an interview.
All right, to make this full 10-step flow super digestible for a whiteboard, let's just chunk it into 2 main phases. Phase 1, the front channel consent. Here is what happens visibly right there in your browser. You, the user, click Login on the client application. The client immediately redirects your browser over to the authorization server. Once you're there, you authenticate, maybe using your password or a passkey, and you get that classic consent screen asking, hey, do you want to let Print Express view your photos? The moment you hit yes, the authorization server redirects your browser right back to the client. But, and this is key, it doesn't send your data yet, and it doesn't even send the access token yet. Instead, it sends back this single-use, short-lived authorization code. Now, what's genuinely brilliant about this architecture is how it perfectly protects your data from being exposed in the browser. That brings us to phase 2, the back-channel exchange.
At this point, your browser's job is basically done. Operating entirely server to server on this highly secure backchannel, the back end of the client application takes that temporary authorization code it just got and makes a direct private request to the authorization server. And crucially, the client also sends along its own client secret. Think of it as a super secure password that only the client and the authorization server know about. The authorization server validates the code, checks the secret, and if absolutely everything matches up perfectly, it finally issues the actual access token back to the client.
So, if you're in an interview, The absolute crucial point you need to explain is why we even bother using this specific multi-step flow over simpler alternatives. Like, why deal with the temporary code at all? Why not just have the authorization server hand the access token directly to the browser back in phase 1? Well, believe it or not, that alternative actually exists. It's called the implicit flow. But understanding the specific system design trade-offs between the authorization code flow and the implicit flow, that is exactly what separates the juniors from the seniors.
See, the implicit flow was originally designed for front-end only applications, the ones that just didn't have a secure back-end server. In the implicit flow, the access token gets sent directly back in the URL itself, and that is incredibly dangerous. It exposes a token to your browser history, malicious scripts, network interception, the whole shebang. The authorization code flow, however, keeps that access token securely hidden safely on the back-end server at all times. Because of that massive security advantage, modern best practices dictate that we use the authorization code flow almost exclusively.
As our sources elegantly put it, the access token provides an abstraction layer, replacing the username and password with a single token understood by the resource server. And that really is the beauty of system design. By using these secure scoped tokens, we can strictly limit exactly what third parties can do with your sensitive data. Plus, we can revoke their access instantly without ever having to go in and change our master passwords.
So now that you've got a really solid grasp on the core code-to-token exchange, I want you to think about this for your next interview or project. Access tokens are intentionally designed to expire super quickly, right? Often in just an hour, just to limit the damage if they somehow get stolen. So how exactly would you architect refresh tokens to maintain a user session in the background when that initial access token inevitably expires, without forcing them to log in all over again? Ponder that system design challenge, and we'll see you in the next explainer.